So today, we're going to see an application and how to use deep learning, and most specifically convolutional neural networks, applied to satellite images, actually radar satellite images, those are SARS images, to identify oil spills in the oceans. So actually, this was a competition from CHOA.ai website. I'm going to also give the link to that, but the competition is closed. But you can download everything from the competition if you want to. So just a little bit about me. My name is Marcelo Gaurido. I'm from Brazil. My background, I'm a physicist, and I have a master's and PhD in geophysics. I worked for several years in the oil industry in seismic acquisition, seismic processing. And since I was in my last year, my PhD, I started to work with data science projects. So I did my PhD with Cruz, so I started to work with data science projects in there. So I went to work downtown Calgary in a few different companies, applied to that. And then I was invited to go back to Cruz and started this Cruz Data Science Initiative. So this is a subgroup inside Cruz that is related to any project about data science. And it's not only on seismic. We do a lot of seismic projects there in the data science initiative, but we do any other, several other projects. One of these are those satellite images. We do a lot of SARS. We do a lot of optimization, production. We do a lot of those different projects related to data science. If you want to learn more, you can go to the Cruz website. I'm just going to click here. There are a few bit more material that you can find this website. Yep. So this is our website in the Cruz. I'm gonna just give you the link in the chat as well. So if you go to the research area and data science, so we do free webinars every 2 weeks. We've been a little bit slow in 2022. But for all the other years, we have done a lot of webinars, usually 1 hour long webinar, and they are all recorded. We can just click and watch in our YouTube channel, as well download all the material. So if you want to learn everything that we have been doing, or at least things that I'm allowed to do by contract, everything that I do, I try to do open source, everything that the contract allows me to do. And there are different examples, both in R and Python. So even in how to build some very nice dashboards using in R and different other applications. So if you guys are interested, I'm just going to copy and paste this link here. So you can download all the material that we have. In 2022, there are a few that are still not available. We are still waiting some approval to make it then available. But we worked a little bit with natural language processing, because we did natural language processing. We are working a project right now where you can extract information from drilling reports and mud logging reports using natural language processing, and use them as data, things that are not widely used in the industry. So those are a few examples of the projects that we do. Also, So that's the CRU's Data Science Initiative. We work with different projects in geoscience, energy, and environmental projects. We also do programming training in Python, R, and MATLAB. And those are the learning labs. Those are the free webinars that we do every week, every 2 weeks. And talking about training, we are going to be starting on February 28th, the second cohort of this CRU's Data Science training, together with the University of Calgary. So this is a programming-based training in data science with the focus to learn everything that you need to learn in data science related to exploratory data analysis, Python, machine learning, deep learning, GitHub, and all those tools that you use in data science, but learning in how to solve problems. So that's the focus, how we are going to be solving a problem. So we're going to be working with a lot of real data that you can find from different industries, as well oil and gas and energy. So we try to open the mind of all the students there and see different applications that they can have on the same method. So if you click here as well, you're going to be able to go to the registration website and learn more if you're interested. And for everybody that is here listening to this course today and wants to join, you can just send me an email. I'm typing my email in here. And you just let me know that you heard this about this course here, and then we are eligible for a 20% discount if you are interested to take this course. Okay, any questions about this?
No questions in the chat. Yeah. So just a reminder to everyone, if you would like to, you can leave a message or a question in the chat window that's being monitored, and we'll make sure that it gets asked. Okay, thanks.
Okay. So now I'm done with my shameless self-promotion and try to sell stuff to you. So let's start with the bootcamp agenda today. So we're gonna give a small introduction to what is machine learning, just to put what deep learning, where deep learning is in it. We're gonna talk quite quickly about our neural networks, and then we'll go a little bit deeper on convolutional neural networks, because that's the part I believe that you guys are more interested in, because I believe you are doing classification in this competition, right, Tim?
That's correct.
Is it classifying the image or pixel by pixel of the image?
That's a good question. I don't, Jeremy, if you can jump, I don't want to give the wrong response here.
Okay, we can see that later. And those are the techniques we're going to see today, and how to apply and try to predict in an image, a satellite image, pixel by pixel, not the whole image, but just the pixels inside there, where the leakage of oil in the oceans is. I'm going to give you a kind of a theoretical explanation and the live coding in the end. Yes, you are still eligible for the discount. And everybody that is here is also eligible for discounts. So just let me know. Just send me an email. Just say, okay, I heard in the SP Datathon about this course. So you are eligible for everybody that's participating here. Okay, so let's start with the machine learning part. So that's the easy part. So machine learning, basically, it's a sub-area of artificial intelligence where we are trying to make computers to think and learn from the data without being specifically programmed for that. So we don't have a fixed mathematical equation there. Let's say, like in physics, we have all the theory there. So we have that fixed. In machine learning, we have some, we can modify stuff there based on the data. So machine learning is actually a sub-area of artificial intelligence. Artificial intelligence is a little bit bigger, larger, because it's also connected to psychology, because in artificial intelligence is actually to make computers think and reason like humans. So it's going to involve other areas. That's not only the programming area. The machine learning are the part of the where you create the algorithm for the self-learning. And the deep learning is actually a sub-area of machine learning. Deep learning is everything that's connected to neural networks, basically. And machine learning is basically divided in three main areas: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is when you have the answer of the data initially, so you can train a model by knowing where you have to get to, and then you can apply this model in the data that you don't have the answer. And this one is divided into two main groups: regression and classification. Regression, it's when our target or our response variable is continuous. And classification is when we are trying to predict categorical targets, like if an image, it's a cat or a dog. In regression would be what's the weight of a person. The unsupervised learning, it's when you don't have the answer initially or never. So there are two main things that you can do: clustering, that's basically grouping the data based on similarity between those points, or dimensionality reduction, that's widely used for visualization, where when you have several features in your data set, you reduce to 2 or 3 for visualization. And reinforcement learning, that's a kind of a combination of both. It's widely used for self-driving cars, where the machine is gonna be learning on the fly by rewards or penalties, depends on the decision that the machine is doing. Okay, so today we're gonna be focusing in supervised learning and in classification, more specifically. That being said, there are actually a bunch of different algorithms that you can find in there. So you have machine learning, you have supervised learning, ensemble, reinforcement, neural network. So for each one of those parts that we have here, there are a lot of different models and strategies that you can use to solve your data. Some of them are going to work better if you have the correlation between your features and your target linear. So you're going to go for more linear models. If the correlations are non-linear, so we have to start to see which model is going to work better, what's the type of features that we have. So we're going to start to make a selection which each model. So if you have a combination of categorical and numerical features, you're going to think to use the tree-based methods. That's going to be a little bit better to use in this type of data. If you're working with images, audio, and videos and all this stuff, you're gonna go for neural networks, for example, and those convolutional neural networks, recurrent neural network for text. And depends on what we are working with, we are gonna be deciding which type of model to use. So there are a bunch of them, and this is not all. This is just a short list of all the models that you can find around. So about the neural networks is a method that it's kind of based in our brains, neurons, where we start to make predictions by connecting our features to those hidden layers and try to make calculations inside here to do a prediction. And it's called a neural network because it's very similar to all those connections in neurons, all those things that you have there, where we are going to be doing calculations by getting our features, for example, multiplying by a weight. Data scientists call weight, statisticians call parameters. They're going to be multiplied by a weight here. and summing with another feature multiplied by another weight, with another feature, summing with another feature multiplied by another weight, and so on. How many features you have, how many neurons you have. You're going to do some calculation inside here. That's the activation function that we do inside to convert this linear equation to a non-linear equation, basically. And then you're going to be sending to the next layer of neurons. So things can get really complex in size, but not that complex mathematically speaking. And there are some nomenclature that we have here. We have the input layer. The input layer is the layer where we have our input data, where each one of those circles represent the features that we have or the variables that we have. We have the hidden layers. That's where the calculation is being done. And the output layer is just the prediction. So if you're doing a binary classification, this would be the probability to be the class 1, for example. If you have multi-class, so you're going to have one vector of probability for each one of those classes. And we do that to make some predictions. So when we have our weights inside here trained, we have to train our weights because we're always going to start out with random weights. And then we have to train our model, knowing in a data set that we know the answer. We can include some input here and make some predictions. Any questions about this?
So far, no questions.
Okay. And the way that a neural network is actually trained is do the back propagation term. I'm not going too deep into that, but if you guys are interested, I have another presentation that I go really deep with the math and how to do back propagation. You guys would be interested by the end of the class today, if you're not so tired?
I think that might be good. Yeah, if we've got time for that.
Okay.
Yeah.
Okay, so you guys let me know. So the idea is that we initially do a for propagation. So we do our first prediction with our random weights. We calculate what is a loss function, basically how wrong we are in our predictions. And then by knowing the amount of error that we have, we do the back propagation. We start to update the weights from the last layer to the first layer. And that is a mathematical reason why we do a back propagation for that. So that's what we saw so far are the fully connected neural networks, where we have simple neurons working with tabular data. Now we're going to start to work with non-tabular data. So that would be unstructured data sets. And because of that, we have to use more complex models. And to deal with images that we are working with today, you're going to be using something called the convolutional neural networks, or CNN. So they are widely specific to work with images in general, but you can also work with them for time series and other applications. And it's basically a model in which we can read an image and prediction, what is this image about? If that's a dog, a cat, or a car, what is this image representing? So we're going to classify the whole image. And the way that the model works is a little bit more complex than the regular fully connected neural networks. We start with our input layer, that are our images that can have from 1 to 4 matrices in general. 1 means that we have a grayscale image. 3, we have red, green, blue. And 4, red, green, blue, plus an alpha for transparency. And what we do, we apply a bunch of convolutional filters in here. Each convolutional filter could be understood as each neuron in neural networks in a fully connected layer. And that's what you're going to be training for, the numbers that are inside those filters. Usually they are 3x3 matrix with some numbers that goes in general from -1 to 1, but you can set that you're going to be filtering these images and creating different filtered images that's going to be sent to this convolutional layer. So from one image, if you have 10 filters, you're going to create 10 new sets of images, each one with a different filter. After that, that's the way that we do convolutional neural network. We do a pooling, that is to reduce the size of the image, because our goal in here is to extract small informations of the image. And we're going to keep, after we reduce the size of the image, we do new convolutional layers and so on. We can keep doing that several times until we have a small representation of all the features that an image contains. For example, if it's a cat, could be the tip of the ear, also a small shape of the eye, and so on. So we're going to try to extract all the small things that all the images contain. And then you're going to send to this fully connected neural network and see which one of them are used to predict if this image is a car, a truck, or a van, or etc. And that's how we pass a filter in here. Each one of those filters, we have our image, that's just numbers that goes from 0 to 255. And we are going to apply this filter in here. That's going to be a rolling window. And they're going to have an output that's going to be our filtered image. And each one of those filters are going to be removing something specifically from this image. We could be removing everything that's horizontal, filtering and keeping only everything that's horizontal, everything that's vertical, all the borders, and so on. So that's our goal when we are doing this type of filtering. And then you're going to be filtering the filtered images, and then filtered the filtered images, and so on, until you can extract just the small parts of this image. So from one original image that we have there, you can create thousands, sometimes millions of new images just for one single image that you have there. And when you are training a neural network, usually we have thousands of images, so you're going to be creating millions of images for each one of those 1,000 images that you have there. So you can imagine how big that can become and how computationally expensive it can be. Okay? Those are, when you have colored images, I believe that's what you guys have in your problem. You have 3 color channels, the red, the green, and the blue. And that's the way that the neural network usually works, is that in the first layer, it's going to apply a filter for each one of those colors, and then just sum them. So only the first layer, that's those 3 channels are separated. After that, they are just put together. We also, can you comment on the impact of dropping the opacity layer in a model? What do you mean the opacity layer? You mean the transparency, the alpha? The alpha in general, I don't believe that's going to bring so depends on the type of image that we have. I don't believe that's going to bring that information, much of information in the modeling, but could be an area that you don't have any object, because if the transparency is 100%, that means that you have no object there in the image. So that would be the information that you can get from this alpha. Make sense? Okay. I never worked with images that contain alpha. I only worked with the maximum of 3 channels. But that's my understanding how the alpha could help. This is what we do for the pooling layers. Pooling layers, it's when we are reducing the size of the filtered image. And there are different ways. You can use the max pooling, the mean pooling, the median pooling, the mean pooling. There are different strategies. The most common is going to be the max pooling, where we're going to go using also rolling window. And for this window here, this 3x3 window, we're going to only be extracting what is the maximum value and only keep the maximum value in here. For the second layer, for the second group here, window, also the maximum number. So that's 4 and so on. So the idea is for us to reduce the size of the image, but also keep with the structure of the image without losing information from what we had the image before. And that's how we're going to be using all the convolutional layers one by one. So we have a number here too. So we have our first layer that's extracting, each one of those filters is extracting a different information from those numbers. And then we're going to apply filters on those filtered images. So we're going to have way more images down here. So another convolutional layer. Then we apply to the dense layer. Dense is the fully connected. And then we can start to make our predictions. So after all these convolutional layers and max pooling, we are going to have something in the middle that is called the feature map, that all the small representations or all the learned features that we could extract from the original image. Let's see if I have an example here. No, I don't have an example here. So that would be just small parts and small representation of the figures. And after that, after we have all these small representations, we're going to send them to a fully connected neural network, the regular neural network that we know. And then we're going to just make the predictions. We're going to send them to the output layer. So this all looks quite complex. Thankfully for us, everything is already programmed and made available for us in different languages. Those are the ones in Python, so we're going to be using TensorFlow today. But you can also learn PyTorch. TensorFlow is from Google. You could learn the PyTorch from Facebook. You have Tiano from the University of Montreal. You have the CNTK by Microsoft, the Turi Create that's now owned by Apple, and you have different frames here that you can work with deep learning. And any questions about this? I think things are going to start to get more clear as we start to go coding.
Yeah, it seems like everything's good, Dr. Gaurido.
Okay, I just asked him to see if I'm trying to induce participation.
Yes. Yeah. So thank you to Dave for putting the question into the chat window. Yeah.
Okay. So let's see what is the application that we're going to be working today. So we're going to be detecting oil spills in the ocean from satellite radar image. So this is also a competition where huge images like that from satellite on the oceans, where we don't have the location in the ocean where those images are. We don't have the coordinates. We just have the images. So they have those huge images. And in a small part here, if you see these small red marks in here, one is small here, maybe one is small here, those where we have these oil leakages that could be by a pipeline, could be by a ship or anything like that. And they have kind of specific shapes like that. So this is a zoomed image. So when you have oil leakage in the ocean, because of the currents, they start to form a line in the ocean. And what is nice from the satellite images, from the SARS image, is that this SARS also is trying to measure, in a way, kind of a movements. When you have oil, oil has a higher viscosity than water, so you tend to have less waves where you have oil in the surface. I'm talking about the small waves. While around, you have a lot of smaller waves. So that's why in the SARS image, the oil, they look like black, and the water, they look like all these messed up and in the gray scale. So that's what we're going to be trying to classify for. We're going to be creating a model that pixel by pixel, we're going to be classifying this is an oil leak, and around here, this is not an oil leak. And those are the kind of masks that were given to us. They didn't give specifically pixel by pixel where the leakage is. They gave us a rectangle. So we know the borders of the leakage, but not necessarily the shape of it. So that's what we have to deal with. And let's see how we can do the modeling in that. The modeling part is going to be a little bit different from the convolutional neural network that we saw. We're going to be using a UNet strategy, where we're still going to have the convolutional layers until we have the feature map down here. But then, instead of just to see what features maps are used to classify an image, you're going to start to localize where those small features are in the image. So you're going to have an output that's going to be another image on the same size of the original image with the probabilities for each object that you have there. So if you are trying to predict 3 objects, so we're going to have 3 probability matrices with the probability pixel by pixel, what kind of object that you have there. In this case, we are just trying to identify the denser. So that would be a binary classification. So we just need one probability matrix, the probability to be 1, the probability to be the denser. And that's what you're going to have today. Those are a few of the predictions that you're going to be able to get today. You're going to see that they are not perfect because our masks, what we call masks, what we have the information about the leakage, it's squared like that, it's a rectangle, but the leakage, it looks like a river. It's just a line in the satellite image. And this green one are the masks that they gave us. Those are the borders that I converted to an image, actually. And the red are the predictions. So you're going to see that the predictions are still not going to be perfect, but they're going to be okay. They're still going to be good to see a lot of those leakage, mostly if they are large. So for today, we have to do a lot of pre-processing of the images before doing any modeling, because those rectangles, they were not given to us as images. They were given to us in a JSON file, only the borders. So part of the work today is going to be creating those masks as well. And that's the cue for us to go for the live coding. Any questions so far?
No other questions. And let's go into the live coding.
So, okay, were you guys able to download the codes in here and the data from the Google Colab, from the Google Drive? That's
I was able to access it. We haven't shared the links just quite yet to the participants, but we'll do that shortly after this session, and also we'll socialize it in the Slack channel as well.
Okay, so you're just going to be looking at me. Good. Because sometimes people want to run together.
Okay, if you give me 1 moment, I will. Oh yeah, either Jeremy is going to drop the link into the chat window as well. Here,
because I can share here quite easily as well. So here's the link. So you guys can download everything that you're going to be doing today.
Great.
So this folder that's going to be shared with you, it contains the presentation that I just showed you today. We're going to have the data. So this data, there are a lot of folders. There is a lot of data. What was initially provided to us was this train data, this train folder that contain huge TIFF images with a lot of pixels inside there. What you're going to be working today is how to read those images in here and converting to small subsets of 128 by 128 pixels. Because our model, a deep learning model, can work with very large images, but then you need to have a very powerful computer to do that. If you want to try to use Amazon or Azure to do these very large images, you're going to be able to, but you're going to expend a lot of money if you're going to try to do this on the cloud. If you want to use your personal computer or Google Colab, like we are doing today, you have to set those images to be smaller. So you're going to be patchifying those images. You're going to be cutting in patches and only saving the patches that contains events. So we're going to reduce a lot the amounts of data that we have for our predictions. And for the codes part, we're going to have 3 codes today. We're going to have the split images and generate masks. So that's when you're going to be reading the whole image and the JSON file, creating the images from the JSON file and patchifying the huge image and save to the disk in 128 by 128 pixels. The second one are going to be suggestions of feature engineering, things that you can do on images to try to improve your predictions. And honestly, everything that I did here, that was a project that I did last year, and all the feature engineering that I did, it did not work, but I still think that's very nice for a learning process to know that you can do things, but they did not work in this specific project. And in the last one is going to be the modeling. But the modeling, just to train our model, is going to take, in the Google Colab, around 4 hours. So you're not going to run the model in here, not going to train the model today. What I did, I saved the models in this folder model in here. I saved it previously. And the model that you're going to be trying today is just this Keras UNet grade 32. So we're going to be using a UNet model in grayscale with a batch size of 32. So that's everything that we have in here. And another thing that I could include that I forgot to include is the report of this project in here. So I'm going to include now so you can download before I forget. So I did a report last year. So just 1 second. I'm just going to upload in here. So together with the presentation, now you're going to have the report and explaining everything that I did basically in the mostly in this, all the step-by-step, all the feature engineering, and the results that we could get. Okay, so enjoy that. Other things that I tried in these that didn't work properly, I tried to do some transfer learning. Transfer learning, it's when you use pre-trained models from the internet to apply in your data. That's something that I'm still working on. And that's something that if you guys are interested, contact me and see how it's doing. If you want to take a look and how to do that, we could do this another day. So, okay, so let's go for the codes. So those are the codes. If I just double click here in one of the codes, it's going to open automatically in the Google Colab. And this is where I have in the Google Colab. And I just crashed my session. And that's okay, because I was just running something here before. And apparently, I crashed. So let me just take a look into the data that we have in here. So the data that you're going to be working initially are those train data. So those are those huge TIFF images. And by the end of it, if I'm not wrong, we also have a JSON file here in the middle of this folder. So that's the JSON file. That's the way that was provided to us with those corners. Then what I did, I just split the image in 128 by 120 pixels, initially creating the masks in here, PNG images, and also the satellite images in here. We are just going to see how to work with them, but in the end, we're going to be using the images from those two folders that I separated, and I did some other process that are not in the code in here. Okay, so let's get started with the coding. So I'm going to be using the Google Colab. If you're using Google Colab and deep learning, remember that it's very nice for you to set the GPU to be available in here. So if you wanted to make the GPU available, you just go to the edit part in here, in the notebook settings, and then you can turn the hardware accelerator. You can just select the GPU. In this case, I'm not using TensorFlow for this first one, only the third one that I'm going to be using the TensorFlow. So we don't need to do a GPU now. But for the third code, we're going to be turning on the GPU. So this data set was actually provided by this Slick in a Haystack challenge. If you click here, you're going to be sent to the challenge website, and all the rules, all the leaderboard, all the discussion. So I believe that I'm not sure if they make the codes available. Let's see the final leaderboard. No, they don't make any of their codes available. But that would be nice if they could make. It's a little bit different than the Kaggle website. I'd like to see what the champion did. So in the predicted and in the final, who won was this Ahmed El Bakri. And this person won $15,000 in this competition. Okay. So now what I'm going to do, I'm going to start running my code. As I'm working in Google Colab and my data is in my Google Drive, I'm just going to mount my Google Drive in here. So now I'll be able to see my drive down here. And everything that I have in my Google Drive is going to be on the drive, my drive, and where I have the codes for today is going to be in the satellite, oil, and the codes in here, and the data in here. So that's how I'm going to be working. And there are a few libraries that you're going to be needing to work today. The first of them is going to be the patch file. This patch file is not automatically installed in Google Colab, so you have to install it if you're using Google Colab. So just do the exclamation pip install patch file, and that's how we're going to be patching our huge image into smaller ones. The next part here, those are the libraries that we're going to be loading. The first one is the CV2, that's the OpenCV. That's one of the main libraries used for computer vision and to process images. JSON, just to load, to work with JSON file. We're gonna have a JSON file that it's very similar the way they store the data there to a dictionary in Python. So if you're gonna work with non-structured data sets and start to work with MongoDB, so we're gonna start to use the JSON files, for example. Also, we're gonna be importing some random functions that's just gonna be for plotting. From the patch file, we're gonna just be importing the function patch file for the TQDM in here. TQDM is only to create a progress bar when we are running a for loop, for example. It's just gonna calculate for us, so we can know how long the for loop is gonna take if you use the TQDM. NumPy for data manipulation. For data visualization, the matplotlib, and to work with directories, the glob and OS. So image files, actually those are TIFF images, not PNG, so I just have to fix this in here. So TIFF images were provided to us. And if you go, that's the location that I have then saved in my folders in the Google Drive. If you wanna copy for yours, for example, you don't need to type by hand. You can just go to where you have there in here, in this file folder on the side here. If you go to the folder that you have your data, for example, this train one, oops, you can just click in those three dots and then copy path. When you copy path, if you just paste in here, so that's the whole path that you have there. So that's a simple way for you to get the whole path where you have your file saved in your Google Drive. So that's where I have the data. That's the folder I'm gonna to load the data from. And I'm just saving here the folder location where I'm gonna save the masks and where I'm gonna save the satellite images. And I'm gonna explain a little bit deeper what are the masks and what are the images when we go through. Also, we are gonna have from the data that we have in here, from this data hood, what is the JSON file? So inside the same train that we have here, we have TIFF images and this JSON file. I think I didn't run this first one, so I have to run this one. So I'm loading all the libraries now. And now I'm just getting all the folders name and the JSON file location. And what am I gonna do next? So that's how I'm gonna be reading a JSON file. So I'm gonna open the file in the read format and use the JSON load. So that's why I imported this JSON. So the computer is gonna know that you are working with a JSON file. When you do that, you're gonna be loading this ground truth features. And that's the file, that's what we have here. So it imports to a dictionary. And in a dictionary, we have a key. That would be this key in here. That would be related to one of those images that we have there. And the borders of our event. So we have one border in here. So in this huge image, we have a bunch of events, a bunch of oil detector. We have this one with 4 corners. Those are the pixels positions in there. We have this other one, and so on. So for each one of those images, so that's the name of the image, because it's exactly the name of the file. If you go back to data and train, so the name of the figures, they are just numbers. So that's how we're going to be connecting those numbers to the JSON files. And we have now this huge dictionary in here. Any questions so far?
No questions in the chat. So obviously you're doing a great job explaining this.
Or they are completely lost. It could be the total opposite.
Well, no one's dropped off, so I think that's a good sign there, Marcelo.
Okay, good.
Yeah.
So now the next step that we're gonna do, we're gonna go to this train folder in here, this folder, and we are gonna list and save it to a list all the file names that has any of these extensions. Anything that's an image file, that could be a TIFF, JPEG, and JPG could be also PNG, but you don't have any PNG in there. So all the figures file that we're going to be doing, we are going to just be getting the file names. So we're going to start with a file name empt, and then for all the extensions that you have there, you're going to be using the glob, and with joining the extensions that you have there. So we're going to be adding to the list all the files that we have that are images. And those are the 10 last images that we have there. So that's the whole location that you can read the image later. So now we can use the OpenCV to just read the image. You just say the location, and you already have the name of the image in here. If you don't select the extensions, you might have a problem because you have a JSON file in there. So this is a way to avoid errors. So now what we're going to do, we're going to start to work and load these data and see how they look like and what we can do initially. So you're going to see that I'm creating a lot of those functions. That's the way I like to do. I like to create functions because those things are going to be quite ready for deployment later. So I'm going to be reading an image. I'm going to be using the OpenCV and then using the emRead. And that's going to be for file names. So for each one of those files, I'm going to be reading the image. I can give this name here, and it's going to read the image. The one thing that the OpenCV does that sometimes you don't pay attention or we don't know is that when they read image, they don't read as red, green, blue. They read as blue, green, red for some reason that I'm not aware why. So what we do here, we are just converting from blue, green, red to red, green, blue, just to make sure that we have in this order the matrices when we load those images. And remember, all these functions that we are creating here, you might be able to use in your project. You might need to do some adaptations, but those are things that you can easily use there. The next one, we're going to be reading the image features. Basically, you're going to be reading the JSON file. From the JSON file, for each one of those images, we're going to be getting what are those corners for each one of them. So we can plot them together. And in this last one, that's where we are reading basically the images. We are scaling them to be a little bit better for us to visualize in here. And also scaling for the features as well. What they call the features here are the target, those rectangles marking where we have the oil space. So here, just make one test. I'm just going to be loading this image using the read image features, and then printing with the matplotlib image show. So those are the type of images that you have to deal with. Those are huge. They are not complete, let's say, in this rectangle. We have clouds in those images, so sometimes the machine could get confused by a cloud because sometimes you have some shadows that are linear, like this one, and our predictor could make a mistake saying this is an oil spill. But it's good to know that we have these, and we have to deal with this kind of stuff. The next part in this code is that we're going to be adding features to the image to print now. Now that you have the full image in here, you're just going to be adding the marks of the oil spills. So that's the same image that you have down here. So apparently this is an oil spill because that's what was marked from that JSON file. So now we can start working. Can someone tell me why this type of a marker for us might not be optimal in our predictions? Color shows, grayscale doesn't. Oh, no, these red marks are just where it's just marking here where is the oil leakage. So usually the oil leakage in the oceans, they look like a line like that because of the currents. So these rectangular shape markers, they are not specifying correctly the shape of the leakage in here. So when you're going to start to do our modeling, we are going to have some problems because you're going to be considering this rectangle as the area of the leakage, not the specific area, because that's the best that we can do with this information in here. So we do the best you can do with whatever you have. Okay. So now the next step is we have those JSON files, we have the borders, but they are just borders. They are just kind of a coordinate. So what I want to do now, I want to recreate this whole image, but for the masks. What we call masks in this image segmentation are the pixels where we have an object or not. So I'm just going to create an image of zeros and ones. Ones are going to be these rectangles, and zeros, everything else. So I'm going to recreate another image with the same size in here, with the same name, but only with ones inside these rectangles. Everything else is going to be zero. So that's the mask. And why are we going to be doing that? Because for the image segmentation, that's what we need to have. This is going to be our supervised learning. This is going to be our answer that you're going to be training our model for. And that's where I'm creating binary masks. So I'm going to be getting what is the image and all the features that we have there for that specific image. So I'm going to be creating a blank image of zeros with the same size as the original image. And I'm just going to be filling with a few convex poly from the CV2 with ones, or in this case, 255, because that's the gray scale color, 0 to 255, or any color. So for all these coordinates, I'm going to be filling there with 255. So when I do that, I'm going to be creating a function. And when I'm testing now, in the same image that we had before, that's what we created. So we converted those red borders now to a mask. So now we know pixel by pixel where the leakage is. And that's what you're going to be using to classify pixel by pixel using our model. But again, those images, they are huge. So if you look to the shape of this image in here, so the name of this, let's see this mask. Actually, that does have shape. So we have 1,588 pixels by 2,000 pixels. So those are huge images to send to our neural networks. So what I want to do, I want to actually patchify. I want to get 128 by 128 pixel windows in here, and getting these small patches of images in here. And then I'm only going to save to the disk those small patches that actually contain oil leakage, because you're going to have, if you don't do that, you're going to have hundreds of thousands of images. In the end, we're going to have a little bit more than 10,000. But if I don't do that, you would have a huge amount of figures to train our model. And for that, it's quite simple. We can use the Patchify library. The Patchify, it was created to patch a large image to the window size that you desire. The way that it's going to work, it's going to create, when you use this Patchify function, you just include what is your image in here, what is the shape that you want for each one of those patches, what's the size of those small images, and the step. So I'm going to do 100 by 28 by 128, but I'm going to be running, doing a rolling window of 100 pixels, meaning that each one those images, they have some overlap. So that's what I want to do. I want to create those images with some overlap, because if we desire to construct back, we're going to have less border effects in our from our neural networks. And the output of this, we're going to include this image that, let me see if that's the same size. I believe it is the same. So this huge image in here that you have in 3 color scales, they're going to be divided into this amount of patches. So we're going to have 15 patches for one side, 19 for another dimension, and each one of them we're going to have this size. Make sense, guys?
It's great.
Okay, if you print just one of those patches in here, so that's how they look like now. So that's one of the patches that contains the oil leakage. So now we have a zoomed image, not zoomed image, we just have that small patch. I looked at one by one until I found it, okay? And we got here. So that's the image, the small patch. And you're going to only be saving those images, basically only when the mask, we have some information in here from the mask. Can someone tell me why I put the semicolon in here? Do you guys know why the semicolon in Matplotlib? So if I run this without the semicolon, I have this message here telling about the access that are created internally in Matplotlib. If you put the semicolon, it is suppressed. So just a curiosity that I like to tell people, because I just learned this last year. Okay, so those are the initial pre-processing that you're doing in those images. You're just preparing the images so far. So what we are going to do now, you're going to create the functions to do this for all the images that we have in this data set, to run these in a for loop. So I'm just going to be recreating some features to read the images and features in here, to create the binary masks. And in here, that's the part that I'm going to be splitting the image and create masks, and they split the images as well. So we're going to be getting the file name, so we're going to be loading from the disk. The idea to have a function like that is that you don't have to load all your files to the RAM memory. You're just going to load, do the processing, and delete from your RAM memory. What is our folder for the masks? Where you want to save? Where you want to save the new images, the size that you want to do the patching, and the steps of the patching. So in this part, we are getting just what is the image number from the file name. Then we are reading what are our images and features from here. Then from those features and those images, we are creating the masks and converting the masks to red, green, blue to save. Because even though those images are grayscale, when you save to the disk, it still needs to have 3 color channels, even though they are just repeated color channels in general. Then we are going to be creating the patches for both the images and the masks in here. Then for all the patches that we have here, and if the mask contains information, we are just going to be saving. If the whole image contains events, then we're going to run this for loop for the patch of the images one side to another. And then if that is inside those mask patches, if there is any information, if the sum is larger than 0, if it's not only an image without any oil leakage, then that's when we're going to be saving our files. And then here it's where we're just going to be printing if we find any file that does not contain any features. And in the end, we're just going to run this for loop in here and to save all these images to the disk. And they're going to be saved in those folders in here. If you go to 128, we just created the masks in here, the folder masks. How many files we have here, I don't know. Let's see. We have 50 images in here apparently, or at least visible. And also for the salt images, those are the images that we just created in here. So those are going to be the output of this first of the first code. Just preparing the data for the modeling still. Any questions so far?
No other questions have come through the chat window.
Okay, I'm not going to run this because it's going to take a couple hours to run. So that's the expected time to run from the StickQDM. If you run in your personal computer, it's going to be way faster. In Google Colab, it's going to be slower because you are dealing with images and files being transferred from one computer to another, and all this stuff is happening there. But here, it's going to take a while. Now we are going to the second part of this course, where we're going to be creating some new images based on the images that we have. In computer vision, there are different ways that you can do feature engineering. You could just flip the image, you could just delete some parts of the image, you could rotate the image, you could shear, you could do a lot of different things in the images in here. And there are many solutions. And what I tried to do in here to try to improve our predictions was something that I thought that was clever, but in the end didn't work. So it wasn't clever at all. So let's go to that. And why do we do that? Why do we do this type of feature engineering in images? There are different reasons. First, could be that you don't have a lot of images in our data set. When you are training a convolutional neural network, it's a very complex model, and we require a lot of images to train it, and sometimes don't have enough images. So we have to create new images when you don't have enough images. It's not as good as have specifically uh, images for that, or fresh new images, but they are impressively good still. Another reason could be to try to make it easier for your model to identify patterns inside your image. Okay, so now I did the same. I just mounted my Google Drive. So this is the second, just remembering. Now we are doing the second code here, this feature engineering. And we're going to start to work with the data. So a few things that I'm going to be loading is the OS, the OpenCV, and the OpenCV, they have they have a EMShow function to print the images as well. But they don't work very well in Google Colab because the way that they do in your personal computer, they pop up another window with the figure. They do not plot inline. So to solve this, the Google itself creates for the Colab dispatches a specific version of the CV2 EMShow that you can actually print the image using the OpenCV. Also the glob for loading the images, and the TQDN for the progress bar. For data manipulation, we're going to be using the NumPy. We're going to be doing some calculations in NumPy, and also from the SciPy signal median filter. So I'm going to try to path median filter 2D in our original image to make it a little bit more smooth and try to avoid those huge variations of color in grayscale. Try to make a little bit more smooth and see if this also helps in our predictions. And in the end, it didn't, okay? So everything that you're going to be doing today, at least so far in my research, they didn't help. But let's see how they work. And also for data visualization, if you want to, the matplotlib and the Seaborn libraries. So just importing the libraries. Now those are the location of my files that I just created in the previous code. Here, the same way, I'm going to be reading those files. And let's see the name of the files that we have there from the save root. That are our masks. Oh, it's inverted here. Well, too late. So I'm just taking a look in how many images I have in this folder. I'm just reading all the file paths that you have there. And sometimes it takes a while for the glob to do that, because you have way more images now than you had before. So this number might not be correct because I had to rerun the code this morning. And as you guys saw, it crashed. So we might have less images than that. But let's see. So we see that we might have a lot of images in there. So actually, we have 11,000 images, 128 by 128 pixels in there. So we're going to be doing the same. We're going to be loading, reading those images. And we're just gonna be taking a look into that. What did I do wrong? So probably I don't have this image in there. Okay, cool. Let me just take this one. Still not. Okay. I see my error. Because here I did for another folder, because I also tried to do my research with 256 by 256 pixels. But I still don't have. So let me just get this one now, because the names might be different because of that. Come on. Okay, cool. It's so nice to have errors, and then we try to figure out what's happening, right?
Yes.
So,
Debugging on the fly.
Debugging on the fly. So let me see. Okay. So this shape rod, those are the masks. So I think I did wrong. So here should be found. Here should be the masks. Oops. So what happened is that when I rerun the code, apparently I have no files there. Is that right? See. So I have 128 because okay, and I also put a wrong name there. So this is set. But train equals okay. So that should be like that and like that. So just fixing my code. Okay, now look like it's working. And what I have to do in here, I should have just to put this as set, and here just the masks. And I'm still having a couple problems. What did I do wrong now? Because the names might not be the same. Okay, and I'm reading in grayscale, so that's why I should have to comment this out. Because when you read as grayscale, automatically the color channel is going to be deleted. So it's going to be a 2x2 matrix, not with the third dimension with the color. So that's one of the examples of the images that we have in here. So that's the name of the image. So we just downloaded, we just loaded again. So that's the leakage that we have in the ocean, and this is the mask down here. So now I think things are okay. So I'm just gonna be saving, and if you download again, it's already updated there in the Google Drive. So now, one of the things that I tried to do to optimize for my modeling is try to make this kind of event a little bit more clear to the machine to look at it. One of the ideas that I had was to do cumulative sums for all the sides. So I'm just going to do a cumulative sum from the top bottom. So where we have this strong black event is going to be, so that would be dragged down for the rest of the image. Also, if you go down over, so from the bottom up, that also would be kind of visible from the left to right and the right left, and then I would average them. So my idea was try to make a cross and to aim exactly in the point where we have a leakage there. That was my idea when I did this. So I did the cumulative sum for the image for the axis 0. So I think it was left to right. For the axis 1, top, bottom, flip upside down. So from the bottom up and left to right. So I try to do them. I just to average them in the end. And I just plot. So this was my result. So the idea was to try to make this black part in here to be a little bit more visible. And that didn't happen. In some images, they become more clear. We see the target going perfectly there, but in most of the scenarios, we don't. So that's why initially this strategy is failing. So that's one of the feature engineering that I was trying. We could try with other images, for example. Let's see how they look like. So this is another image. So we have this black spot here that's quite clear in this image. When we do this type of cumulative sum, so that's what I was trying to mark. So this area here, this block starts to become a little bit darker. So that's what I was trying to do when I was doing these cumulative sums. I was trying to make this area a little bit more clear, like a target inside the image. Like I said, in a few images, they work more or less nice, and in others, it didn't work at all. Another thing that I tried to do, I tried to apply a median filter. So the original image would be a little bit more filtered out like that. So all these variation of colors that we have in here, you see that we have looked like a sand box in here. It becomes a little bit smoother down here. So the blacks area start to be a little bit more clear compared to the neighbors. So that's the idea, to try to pass a smooth filter like that. So that's one of the feature engineerings that we were doing. We could try using this median filter 2D. Different sizes of the window. You could try a smaller size of the window, for example. So the smooth is going to be a little bit weaker. We could try a larger window. So it's going to be stronger, the effect. So if you have small events, small leakages in the image, so you might start to actually filter them out. So we could create as well several of those feature engineerings with different levels of those filters as well. And how we're going to be using them in the image in the end? Well, we have a grayscale image that have just one color channel. But TensorFlow doesn't tell us how many color channels we can have. We can have how many color channels we want to have in TensorFlow. So we can add each one of those created features, these created images in here, as a color channel. So the first one, that's going to be the red, is going to be the original image. The green could be this one. the blue could be this one. We can have a 4, a 5, a 6, a 10 color channels if you want to. We can add different filters and different feature engineering generations in those color channels. That's something that is good to know about TensorFlow. We don't have a limit for color channels, so you can add all those strategies there. And that's what we are doing. We have those images that they are basically grayscale. So they have only 2 dimensions. Just remember, if you do the image dot shape, it's only 128 by 128. But when you use this NumPy to expand dimensions and create a third dimension, remember that numbers in Python starts at 0. So we have the x is 0, x1. So this is x is 0, x is 1. So we're going to be just expanding, creating a new axis 2. So when you do that, with this image, the output from this, that is the image underscore RGB shape. So I just created this new dimension in here. It's just one because we just actually have one dimension. But we did the same for when we did the median filter and the cumulative sums in here. So what we do, we're just going to concatenate them all together in the axis 2, in the third axis. And then we created a RGB image, but with each one of those information telling something different. So we have the original one combined with the smooth one plus the cumulative sum. So the cumulative sum is actually telling us something, because the parts where we don't have the leakage technically should be telling us something. The part where we don't have leakage, it's more red, and the part where we have leakage, it's less red, basically. Make sense, guys? If you use here, I believe the PLT, show, I think it's gonna be better. Or don't. Nope, I didn't like it. Can I control the figure size? Probably have to do before. PLT dot figure. Let's see. Size. Let's try to make it a little bit larger. 8 by 8. Let's see if it works. No. So yeah, so that's the idea for the feature engineering that we are doing. I only tried those 2 that are actually in TensorFlow. You can do different ones. If you go for the data generator in TensorFlow, oops, TensorFlow, you have the image data generator. So you have this function in here that you can use in TensorFlow, that you keep your images on the disk, and you can load them, and for randomly, you can apply a bunch of different pre-processing. You could, for example, rotate the image up to the angle that we have in here. You could brighten the image, change the color. You could shear the image. You could zoom the image. You could do horizontal flip, vertical flip. You could rescale. You can do a lot of things using this image generator. And that also helps a lot for the modeling part. And to run, you can actually use straight from the disk. If you use a flow, meaning that you loaded everything from your to your RAM memory, you can do a flow from directory, then, oh yeah, thank you. Then you can actually read from the directory. Each one of those files is going to be reading one by one, might be doing or not some of those feature engineering and train the model. And you're going to be doing that during the training process. It's quite powerful. And I really recommend for you guys that you're going to be doing this type of a classification to take a look into this documentation. And if you have any questions and how to make this work, again, just let me type again because I saw that some people came later. This is my email. If you need help, you can send email and you can talk to anyone in the Slack channel. And now what I decide to do here in the end is to make this ready for production. And again, I just create functions. I do everything in function. Now that I did a test, I'm going to do that for all the images that I have in my dataset. So I'm going to read and normalize the images. I'm going to make all the images to have a minimum 0 and maximum 255. Then I'm going to apply the cumulative sum. And here it's where I apply all the methods in here. We're going to be applying the read the image, to apply the median filter, the 4-directional cumulative sum, and concatenate them in one single image. So I could create them. So I could read just one file in here. And let me try another number. So that's another example file. So let's see another number. This is a bad one. Yeah, so this is one of the files that we have here. You could try different median filter. So this is automatically gonna load, gonna apply the filter, gonna apply the cumulative sums, and then save in one with 3 color channel images. You could try, I don't know, 1,000. We have 1,000 images in here. No. So we have 300. Yeah, so those are a few of the files that we have here. We'll just try a few different ones. I'd like to see one. So this one apparently has some oil leakage, but it's not clear. So that's why these methods didn't work properly. And in the end, that's the area. Basically, that's when I created those functions just to save to the disk. Now, so I'm not going to run this because, again, it's going to take a couple of hours. But that's what we're going to be doing. We're going to be running for all of them, and they're going to be saving to the disk. And when we do that, in the end, we're going to have those images that now they are inside those test and train folders. So let's look into this train. We're going to have the images and the labels. The labels are going to be the masks. The images are going to be the augmented images. So from the images, we have the augmented images. And that's how they're going to be looking like. So we can read one of them just to look. And those are the augmented images. And those are the ones that you're going to be loading to create, to train our model. So we are done with this feature engineering part. Any questions?
No new questions in the chat window.
Okay. So then I'm just going to save this. If you guys want, you can download this code now as well, because I had to update. And let's go to our last part then. That's when you're going to start to train a model that you're not actually going to run, because it's going to take a few hours. We are just going to load the model that we saved. So now the modeling and deep learning. And you're going to learn how to work with TensorFlow now. Do you guys have experience working with TensorFlow for Python?
If you have used TensorFlow, maybe you can just drop that into the chat window. And then we'll look at that as you continue on.
Okay.
A few yeses already. Yeah.
I see that some people yes. Okay, good. Not so much. So we're gonna go quite quickly into that. If you wanna learn a little bit more, again, I'm just gonna show another code that I did image segmentation. So in the Cruise website again, if you go to the research link to the data science, and for the webinars in 2020, I did want to try to identify salt in seismic images. So if you go here, we have the webinar. That's, again, a recorded video where I try to explain step by step how the TensorFlow works for this type of models. It's going to be a very similar model that you're going to be trying today. And also download all the codes and the files that you need for it. So I'm just going to copy this and paste for you guys. So a little bit more documentation and how to work with TensorFlow. So now we are going to be doing modeling. Remember, modeling is something that's going to be computationally very expensive to do for deep learning. So the first thing that I would recommend is for you guys to run these on GPUs. GPUs are fast processors, and Google Colab, they provided us with free GPUs to use. So you can go, when you have a Google Colab and you're connected, you go to the edit on the top left, to the notebook settings, and the hardware accelerator, you can choose the GPU. You also have TPUs. Technically, TPU should be faster than GPUs, but then you have to do some tweaks in the code. It's not straightforward to use TPUs. Those are the tensor processing units. Those are specifically for deep learning. But let's stick with GPUs because it's a little bit simpler to use. And they are way, way faster than CPUs. So I'm going to be doing the same. I'm just going to be mounting my Google Drive. So initializing, I'm connected. Again. I actually have that Apple with the M1 chip, technically that was made for machine learning. They have GPUs inside the CPUs. And I'm going to say that they are faster than running in the Google Colab. When I had to train this model, I could train faster in the Mac than in here. So if you guys have that M1 chip, it's going to be better than using this Google Colab. Unless you pay for the Google Colab Pro. And then that's another level. Okay, so now let's start building our model. And that's how we do in TensorFlow. We actually have to build the structure of our model step by step. If you guys are used to use scikit-learn, that's going to be totally different. You have to set the whole structure of each one of those layers that you want. So to load and plot in the images, the OS and the OpenCV that you're going to be loading, Matplotlib and Seaborn for data visualization, and NumPy for data manipulation, and random just to create some random images in the end. And for the machine learning part, just from the scikit-learn, I'm just going to be selecting a train test split to evaluate our model in the end. We're going to be importing TensorFlow. And from Keras, so if you guys don't know, Keras was a separated package than TensorFlow. Keras was created by Colette in the early 2000s, if I'm not wrong, and it was used to be an interface for TensorFlow. Because the first version of TensorFlow, it was not user-friendly at all. It was quite complex to use TensorFlow before. So Keras was kind of a wraparound for the TensorFlow. And not only for TensorFlow, was also for Theano and the CMTK. When TensorFlow came to the second version, the TensorFlow 2, TensorFlow became way more user-friendly. I believe a little bit because of the competition for the PyTorch. And they included Keras as one of the models inside the TensorFlow. So we're going to be using the same type of libraries or functions that we used in Keras separated, but now we can directly load them from the TensorFlow library. So in here, you're going to just be loading different functions like model and the input. That's going to be for the input layer. And this is to create our final model. Also from the models, the load model and the save model. If you want, we're going to be saving our model and load from the disking. So this one we're going to be using today. We're also going to be loading different layers that we have for the convolutional neural networks. We're going to be loading the max pooling when you're going to be reducing the size of the image, the convolutional layers, that's where we are applying the convolutional filters, and 2D, because we have 2D images. The dense layer we're not going to be using. A dropout is a layer that we include inside those, in between those convolutional layers in general. This is to avoid overfitting, to make our model to be a little bit more stable. Same as the batch normalization. So those two are to regularize our model. We have this comb 2D transpose. That's when we are doing the inverse part of the filters, and you are trying to pin where those extracted feature maps are in the image to calculate the probabilities. That's the part when you are increasing back the size of the image to end up with a matrix of probabilities. The upsampling, that's going to be the inverse of the max pooling. Some activation function, and to add them, and to concatenate, because this concatenate, we have to concatenate the output of some layers to the input of others for this UNet model. And this image data generator, we're not going to be using today, but that was some of the tests that I did in the past. So we're going to be loading all the libraries. And here, we're just checking if you have a GPU available. And yes, as it showed the name of the GPU, the column 0, so we have a GPU available for us. Now here, we are just setting what are our data that we have in here in the training side and the test side. Remember that for the training and for the masks and the images, they are in different folders, but they have the same name. So one image in the augmented images. Oh, we have inverted here again. So let's see. So I think I have them inverted in here again. So here should be the AUG image. And here should be the masks. Same here. I have to run this again. Because of that, And oh yeah, and here I have to change as well. Images and labels. Oops. So let's go and read all the file names again. And here we're just gonna see how many images that we have. We're gonna have more than 11,000 images in the end. And while it's loading all the files, that's how we're gonna be reading our images. From the training data, from the augmented images, like I told you, our feature engineering didn't work properly. So I'm just going to be reading the first channel, the first color channel, and the first color channel is just the original image, 128 by 128 pixels. So that's what I'm doing here. And for the color, for the masks, I'm just reading in grayscale. And for both of them, I divide in 255. Do you guys know why I divided by 255 the images? Do you guys have an idea why? This is because the colors that we have, they go from 0 to 255, all the colors. And TensorFlow like to work with numbers that goes from 0 to 1. So we are just normalizing the numbers in those images to be from 0 to 1. So that's why this specific number, 255. So we have 11,000 images. So what we are going to do now, we're going to load all of them to our RAM memory in here. Because they are quite small, they're not going to use a lot of space. So we can actually load them to our RAM memory. So that was one of the advantages to save those images in 128 by 128 pixels. That might take a couple minutes to read. Meanwhile, do you guys have any questions?
No new questions in the chat.
Okay. So when we read those images, getting only the first color channel and in grayscale, they're going to have a shape of 128 by 128 without any color channel. Even though that grayscale is just one color channel, TensorFlow requires the color channel information. So that's why we have to expand again for the color channel dimension. In this case, it's going to be the dimension 3, or actually the dimension 4. Because you're going to have, those arrays are going to be, each one of those images, we have 11,375 images, 128 by 128 pixels, and one color channel. So we're going to have this 4D matrix representing our data. So it's still reading, but luckily I had run this before, so I have all the outputs in here already. So actually, we don't need to run this code. We can just look at the outputs. What I did here was to separate into train and test, getting 20% of the figures to be for the test side. And that's how we are going to be creating, let me see where we are. And that's how we create a model in TensorFlow. And that's going to be a quite complex one. I believe that we jumped to the part that we build a very regular convolutional neural network, and we jumped straight to the UNet. And that might be a little bit confusing, might be a lot to digest, but try to bear with me. And that's how we build. I'm building, I select to build in a way to be a function. So I'm creating a function that I'm going to generate this model in TensorFlow. So I don't have any pre-trained weights, and that's going to be the input size of the images that I'm going to have in here. Could be 128 by 128 by 3, 128, 128 by 1. You select, this is the default value. I'm going to select to have only one color channel later. So I'm just going to create the first layer. So the first layer is going to be the input layer. So when we look to regular neural networks, for example, like this one, the input layer would be equivalent to this first layer in here, where we just have our input data. We're not doing any calculation. We just have to say what is the size of the image, not how many images that we have there. And then we're going to start to do our convolutional layers and all our calculation. So you're going to see in the literature and other examples that it's very common for people to create those models in blocks. So we have our first block where we are working with images with 128 by 128 pixels. So for each one of those images that we are inputting, we're going to send to a first convolutional 2D window. We're going to be applying 32 different filters. They're going to be randomly started. That's what we're going to be training for. What are those numbers inside of those filters? We size 3 by 3. An activation function. Remember that I told you that you need to have an activation function inside a neural network to convert a linear problem to a nonlinear problem. And we are using the ReLU, the rectified linear unit. And what this activation function says, that every number that's negative is going to be set to 0, and every number that's positive is going to be equal what it was before. It's just a transformation that you're doing here. We are also padding. So for people that work with images, know that when you apply convolutional windows, we might have border effects if you don't do any padding. Padding is basically including out layers of zeros in image. So when you pass a rolling window, you're going to end up with an output image with the same size as the input image. And this is the kernel initializer. So this is just a smart way to do initialization of those filters. They are not going to be that random. They're going to be dependent of the data. Actually, they're going to have a normal distribution. That's why it's called normal. And then that's the kind of the one of the options that you can create those models. And that's one of the way you will do. You're going to apply these convolutional windows in here. In those inputs, these inputs are the ones that you created in here. So you're going to create this one. You're going to be sending to be applied to this one. And that's going to create this object that's going to be our first convolutional window, or our first convolutional layer for the block 1. And then we are going to be sending this conv1 to a batch normalization to stabilize our modeling. And we're just going to be overwriting. And then we're going to be doing this process. We're going to send to another convolutional 2D. So in the first part, we created 32 images in here, plus a bias. So we have 33 objects in here that we created. And then for each one of those 33, you're going to apply another 33 objects in here. So basically, we're going to have 33 times 33 images created only this step. And each one of them are going to have 128 by 128 pixels. So let's do just the calculation 32 by 32, 32 times 32. So only in this first layer, oh yes, because it's still loading the data, so it's not going to be doing the calculation. I can just do a calculator. Because I'm terrible to do counts in my head. lately. So let's just do 32 by 32. So only in this part here, we already created for only one figure that we input more than 1,000 figures. And remember, we have 11,000 figures. So if you multiply this by 11,000, so we would already have 11 million figures in just this first layer. So you can see how memory consuming this model can be. So that's why you cannot read those 11,000 images all at once. What we are gonna do, we're gonna do all those ones that you created, and we're gonna read just a small portion, let's say 32 images. Those are called the batch. And then you're gonna create 32 images. And then that's when you're gonna, all these that you're gonna send to the next layer. After we do a max pooling, now we're going to be calling this pool, and then we are reducing the size of the image in 2 by 2. So what was 128 by 128 pixels now is 64 by 64 pixels. And then we're going to include another block of a convolutional neural network windows and batch normalization and reducing the size of the images. But one strategy that people usually use when they have smaller images, now here, you use more filters. And as your image is going to be decreasing in size, you're going to start to add more filters, more filters. And you're going to see also that people like to use this power of 2. I don't know if there is actually an advantage for that, but it's very common for people to use like 8, 16, 32, 64, 128, 512, and all those numbers that are power of 2. So we're going to keep reducing the size of the image and create all the feature maps that we can until we have the center part where we're going to have small images that contain only 8 by 8 pixels. And then in this part here, it's when we are going to start to do the upscaling. So that's the decoder part. The first part here is called the encoder, that we are just extracting all the features that we have the image. And the decoder part, it's when we start to localize those features inside the image and calculate the probabilities for them to belong to a class. We start to do this conv2d transpose, so we're going to be increasing the size of the image from the output that we have in here. Then we have to concatenate them after do the batch normalization. That's going to be a merge. We have to concatenate them with the conv3. So when you have the 32, the 16, here. That's the first one that comes from the center. We have to concatenate with the dropout of the 4. That would be this one. So we have to concatenate the output of this layer with the input of this one. So that's when we are going to get extracting all those features there and localizing in the images that we created from the filters there. So we're going to be doing the inverse process. We're going to be separating all these features in small pieces, like we have 1,000 cars. And then we separate all the pieces that we have in all the cars. And then we are trying to assemble them again. That's what we are doing in this decoder part. We are just assemble everything again until we're going to end up with a single matrix of probabilities. That's why we use an activation function named the sigmoid. Those are going to be the probabilities for this pixel to be 1. Meaning, what's the probability for this to be oil leakage or oil spill or not? Now that we created this, we have we create our model in UNet, saying what are the inputs. The inputs are going to be this input layer, And the output is going to be this last layer here, containing all this information that we created in this model. And then from this function, we're going to just return this model. Any questions about how to create this model in TensorFlow? Probably no, probably yes. Let's see. Message.
No, it doesn't seem like there's any questions, but I did drop a message for the attendees. Just as I noticed, some people are starting to drop off. This course does qualify for a digital credential. That's one of the features for this particular Datathon, is to provide all of our participants with a digital, personal digital wallet. So there's a link there that will take you to a form that you can complete to receive your digital credential for today's course. Okay, thanks for that, Marcelo.
Okay, thank you. So here is just how we create the model. So when we do that, we create a model, but we also have to compile this model in TensorFlow. And in the compile part, that you're going to say, what is our optimizer? Our optimizer, it's how we are going to be solving for the minimization and the update of all those weights that you have there. If you guys want to stay a little bit later, I'm going to explain how the backpropagation work and what this atom stands for. What is the loss? What is going to be our cost function? So we have a binary classification, and it's going to be, so for TensorFlow, for classification, it will be the binary cross entropy. So that's the objective function that you're trying to minimize for. And the metric that you're going to be monitoring while we are training is going to be the accuracy. So we create our model. In this case, I'm creating only one color channel. The UNet from the function that we had above. We're going to compile the model, and you can print the model summary. So you're going to have the information for each one of those layers that you created, how many parameters that you have. Those parameters are how many weights that you have to train for, or non-trainable, you decide, and you have a very large model. And we have to train for more than almost 8 million weights in here. If you remember from the machine learning, if you try to train for a linear regression, the number of weights are just the number of features plus a bias. Here, we have 7 million to train for. So that's why it's very costly. And this is just for one image, okay? We're going to be doing that for 11,000 images. So that's why it takes too long. That is also from the TensorFlow keras. You can actually plot the model. You can actually look at the model and how it goes step by step. So we have our input layer, what are the size that we have in here, and then we have a convolutional 2D, and how many elements we have here, and then another convolutional 2D, and then you see that you have another arrow come down here, because after the max pooling, before we do the max pooling, you're going to be sending the output of this layer to the input of the last convolutional blocks in here. So that's when we're going to start to localize where our features are. And that's the whole draw of the model that we are creating. So that's the whole structure that you created for this deep learning model. So it's a quite complex one and a quite long one. And even though it's a quite long and complex one, you'd say that's not the best one. You can find, this is a very simple solution for this problem. I was able to train it in my Mac in 2 hours, 2 hours and a half, more or less. But that's not the optimal solution that we could get. We could get way more complex model and finer structures that might work better in this scenario. And that's how we are going to be training. So now it's going to start to look a little bit more similar to the scikit-learn. After we create our model with some of the hyperparameters that we want in it, now we're just going to use the model.fit in the end. There are just a few things that I do in those type of models. I use some callbacks that are available for TensorFlow. The callbacks is just a few things for you to stop earlier the training if you're not improving, to save the model at every iteration, to save at the disk. If you have a crashing, at least your model is saved at the disk, or only to save the best model. Because sometimes those deep learning models, you're increasing accuracy, suddenly starts to decrease. So we're only going to be saving the model that we have the best accuracy, for example. We might have this type of curves for each one of the iterations that we do. So the early stopping, it's saying that if after 5 iterations, the monitor here, that's my validation accuracy from the validation data set, doesn't improve, so I'm going to stop running. I'm going to stop training. And the model checkpoint is to save the file, all the information of the model to the disk in this location. So that's the model that we actually created in here. So that would be this model. That's actually a folder that contains all the information about the saved model. We're going to be saving them in here. And then you can load it later. We're going to be running this only for 30 iterations, and the batch size is going to be 32. So we're going to be loading 32 by 32 images only, and training our model, and then loading another 32, and then another 32. We're going to be doing small steps because you don't have enough RAM memory to do for all of them. If you look to the RAM memory for the Google Colab that they provide to us, they provide to us this amount, 12.7 gigabytes. So if you want more, you can upgrade to Google Colab, but most of the scenarios, I never needed to use a Colab Pro in my life. And when we start to run your model, then we have to do the .fit. We have to say what is the our data. So that's going to be all the images that we have. The Y are going to be the masks that we have for each one of them. What is my validation data? That's the one that I did in the train test splits. The number of epochs, the batch size, and the callbacks, those callbacks that I created up here. So it should be inside a list, all the callbacks that we have. And when we start fitting the model, those are the type of outputs that's going to be shown here for each one of those epochs, that's also called the iterations. It's going to be printing what are the laws that we have. That's the binary cross entropy. What's your accuracy? This is for the training data set. And also, you're going to have the same information for the validation somewhere here, actually. That would be here. We also have the same information for the validation dataset. And you're going to see that for each epoch, this validation accuracy might be jumping. In this case, it's jumping up and then going down. Sometimes jumping up, going down, and jumping up. So when you plot this information in here, so for the TensorFlow, when you are training the model, you can save all the information about the training in this history object that's going to be similar to a dictionary. And then you can extract some information. What is the loss? What are the validation laws for each one of those epochs, the accuracy and the validation accuracy? And we can plot them. So we see that the loss was mainly decreasing for the training data set and for the validation when we start to diverge in some points. Same for the accuracy, was increasing and then it starts to diverge. So probably our best model would be something in the epoch 5 or 7. And that's probably the file that we saved in here. So our last saved file was this one on the epoch 8. So apparently I'm still reading those images. Probably I should have done that. Oh, I mean, I need to do that, but it's still taking a while to read all these images. Now that I know that my best model is from the epoch 8, so probably it's this one. No, should be this one. It's just because it's starting at 0, but should be starting at 1. So it should be this epoch here. I'm just going to be loading this best model with the weights that were trained in here. Then I'm going to calculate the predictions for the validation, and then I could print them. And those are the predictions that we could get from this simple modeling. So I'm randomly doing some plots. That's the same that we have in that PowerPoint presentation. So the red are the predictions, the green are the true masks, and we see that our predictions are doing way better, actually, than the rectangle. We are actually trying to make pixel by pixel predictions in the darker area and around it, not specifically in the rectangle area. So our model is working nicely. It's still not perfect. We still need to do some research and how to improve it. And but that's how we did all the process to start with very large images, complex images in a JSON file. We did all the work and how to pre-process our images, save them in small batches of images, and then how to do the modeling. Technically, a modeling that's way faster than doing those very large images. So we're still loading the files there. So any questions so far? So we are still loading the file. So that's something that I actually didn't train in the Google Colab. I trained in my personal computer because of this. So any questions about these guys?
No questions in the chat window. Oh, wait,
I might have missed it.
Mm-hmm.
But what is the output from your machine learning model? Was the intent to convert pixels to a volume? So the output in here actually is going to be a matrix of probabilities to be 1. So it's going to be a matrix that contains values from 0 to 1. And we're just going to say that probabilities larger than 0.5 is 1, or you can change another threshold, and below that is 0. So my output in here is just going to be one matrix of probabilities to be 0 and 1, because you just wanted to classify one class. So what's the intent to convert pixels to a volume? So not in this case, we don't have a volume in this case. I actually worked in a project that we are trying to do, we are doing this same type of image segmentation, but to classify faults on seismic images. And then we are working with volumes. And that's when we had the 3D volumes to work with. But in this case, we have only 2D images. Does that answer your question? Okay. Because basically for what I wanted to show you guys today, that would be it. I just would like to thank you all for being here. If you want to stick around a little bit, so this is just my information. If you need to contact me, I have my email, in the University of Calgary. So that's the cruise website. So it's in your presentation if you download. If you need to contact me, if you wanted to learn more and to learn more about the course that you're going to be giving in February 28th. Remember, you all guys are eligible for the 20% discount. Just send me an email.